Hi everyone, today I'd like to talk about pipelining in hardware. HLS tools today have now been widely used in custom hardware designs. The users can easily get efficient hardware designs by inserting some HLS parameters. One of the most popular parameters is pipelining, which exploits parallelism among iterations. The initiation interval is defined as the number of clock cycles between two consecutive iterations. When an II is greater than 1, the hardware performance may be poor. In most cases, the users cannot do anything about it. Some code transformations may be possible, but they are still quite limited. Today, we're presenting a new approach to reduce these IIs using dynamic CSlow pipelining. First, let's revisit hardware pipelining. Here is an example of pipelined hardware. Each circle represents a hardware operation, and each square represents a register. The edges represent the flow of data. Now, say I have an input. It reaches the first register in the first clock cycle. In the second clock cycle, it is forked into two tokens in the hardware. One represents the beginning of the second iteration, and the other represents the second stage of the first iteration. So these two iterations are executing in parallel. Similarly, in the next clock cycle, the third iteration is executing in parallel with these two iterations. For this example, the II is 1. And we assume that the critical path of the hardware is T. The overall throughput is then 1 over T. Now if I replace each register with two registers and evenly distribute them in the data path to reduce the critical path, it then takes 2 clock cycles to start the next iteration, also known as II equal to 2. And there is always one register idle in the cycle. However, if a second input arrives at the hardware, it is still blocked until the first input finishes the computation, because the hardware cannot determine the absence of dependence between these two inputs. We then have an II of 2 and an approximately halved critical path because of the additional registers. The overall throughput remains 1 over T. This is known in hardware pipelining that adding more pipelining stages may not improve the overall performance in time. On the other hand, CSlow pipelining is a technique that adds more registers but also improves the hardware performance. It was initially proposed in 1983. However, it is not yet supported by any HLS tool. In CSlow pipelining, it is assumed that each input to the hardware is an independent set of data. Then after the first input enters the hardware and starts iterating, the second input can also start computation, filling into these idle registers. Dynamic CSlow pipelining allows the second input to enter the hardware whenever it arrives at the input and the first register is idle, rather than statically scheduled. If there is no available registers to hold the data, then the next input is blocked until one of the executing inputs finishes. The outcome of CSlow pipelining is that the independent iterations executed out of order. For example, the green token starts before the last iteration of the red token. The overall II of the hardware is now 1. Like the previous example, the critical path of the hardware is nearly halved because of the additional registers. Then the overall throughput is nearly doubled compared to the previous example, which is 2 over T. And C equals to 2 in this case, as each register is replaced by 2 registers. Okay, so CSlow pipelining is very helpful, but how do we integrate it into HLS tools? The synthesis flow of HLS tools are mainly three steps. First, in the front end, it analyzes and optimizes design at source level, such as array partitioning and loop unrolling. Second, in the back end, it either statically pipelines the design or creates data flow graph for dynamic pipelining to exploit parallelism in hardware. Finally, it generates RTL code as the final design. But where should the CSlow pipelining be carried out? We solved two challenges in supporting CSlow pipelining in HLS tools. First, we show how to use hardware transformations to generate efficient hardware to achieve CSlow pipelining. Second, we propose an approach that automatically determines the code regions that are amenable for CSlow pipelining by checking the loop minimal dependence distance. We use an open source HLS tool named Dynamatic for prototyping because Dynamatic generates data flow circuits that have similar architecture as the pipelined hardware shown before. We add an analysis plugin in the front end for analysis and an optimizer in the back end for hardware transformation. Here, let me walk through a simple example. Now I want to get an efficient hardware design from the code on the left. The code is a nested loop that processes array data in B and updates array A. Function f, g, h are some simple arithmetic operations, which are not important for now. So what should I do? The first thought is to pipeline the loops. However, we have two issues here. First, the inner loop has a variable loop bound, making static pipelining of the outer loop impossible. Okay, let's try dynamic pipelining. Then the second issue is that in the inner loop, the variable s has a carry dependence on its last iteration. The dependent operation has a latency of 3 cycles, leading to a minimal loop II of 3. And here is the pipeline schedule of the code. Although the outer loop is pipelined, where the second outer loop iteration executed in parallel with the first outer loop iteration, the overall II is still 3 because the dependence on S. The original control flow graph of the code example is shown here. Each basic block contains the control flow and the data flows. The data flows are hidden here as they are already pipelined. The control flow triggers the data flow when the base block starts. Let me walk through this example. A token enters the header of loop 0 and triggers the data flow in that base block. Then it reaches loop 1. It iterates inside loop 1 until the exit condition holds. Then it goes to the lower block and starts the second iteration of loop 0. So we can intuitively see that there is always at most one token in the control flow. The dynamically CSlowed hardware is shown on the right. A loop scheduler is configured with C equal to 3 and inserted to enable control flow parallelism. Now when the token reaches the loop scheduler, it triggers loop 1. And the scheduler also generates another token to the lower block to early start the second iteration of loop 0. Then the second iteration of loop 0 starts its instance of loop 1 in parallel with the first iteration. And the third iteration of loop 0 has also started. This repeats until there are 3 tokens in the inner loop, and the fourth token is blocked by the scheduler until the first token exits the inner loop. Since the execution of different instances of loop 1 is out of order, the order of the tokens exiting loop 1 may not be in the original program order. The loop scheduler holds the exited tokens and reorder them as the original program order to ensure correctness. It enables dynamic CSlow pipelining by checking the entry condition and exit condition at runtime. When the tokens exit loop 1 in order, the next tokens then enter loop 1 to iterate. For this example, C equals to 3, and there are at most 3 tokens in the control flow of loop 1. The detailed design of the scheduler is explained in the paper. The execution order has now changed as loop 0 iterates early. This is only true when the early executed iteration do not break the original dependence. Here we use Microsoft Boogie to statically prove that the transformed execution order cannot break any dependence. Boogie is an automated verifier that translates its own verification language, also named Boogie, to SMT queries at low level. This allows the high-level program to be reasoned and verified automatically. The users need to translate their specifications to Boogie programs for verification. For this example, if C consecutive outer loop iterations are executing in parallel, then these C iterations must not have any dependence. This means that the minimal dependence distance of the outer loop must be at least C. For this particular example, our tool translates the input program into a Boogie program. Here we don't need to look into the details of the Boogie program. The Boogie verifier automatically finds that the specification always holds for any C no greater than 6. This leads to 6 design points for these Cs. Okay, so how much performance improvements can we get? This figure shows the performance of the example over different Cs. The performance is significantly improved when C is less than 4, because more tokens are parallelized in loop 1, filling into the unused pipeline slots. But the performance does not change for larger Cs. This is because the original IR is 3. All the unused pipeline slots have been filled. Further, early executing more outer loop iterations does not cause any more parallelism in clock cycles. We also evaluate the effectiveness of our approach on 8 benchmarks. We collect the performance of hardware generated by Vivado HLS and Dynamatic. Although Dynamatic uses dynamic scheduling to achieve a better performance in clock cycles, the clock frequency introduced by the additional handshaking signals make the wall clock time worse. Our approach further optimizes the throughput of the hardware in clock cycles, which leads to significant speed up compared to both Vivado HLS and Dynamatic. On average, we have achieved 2.9 times speed up with only 7% area overhead by inserting the loop scheduler. In conclusion, we propose an approach to bring CSlow pipelining to the HLS world. It checks the absence of dependence between consecutive outer loop iterations and parallelize them if they are independent. The HLS tools today have various techniques to optimize the hardware performance. We hope our work can further push the limits of HLS tools, closing the performance gap between HLS designs and manually optimized designs. Thank you. Now I will take questions.